So we've been talking about limits and how they relate to continuity and differentiability, but our real goal is being able to find the maximum or minimum of a function. So we want to find the extreme points, or see, the plural of an extreme would be extrema, so the extremes of a function, so the highest points and the lowest points. And I want to look at a bunch of examples, and I want you to notice some patterns that are occurring in these functions. One thing I want you to notice is that if a function is continuous on a closed interval, then there's always going to be an absolute max and an absolute min. So we'll have absolute extrema. Now, for my first example, I want to talk about the difference between an absolute extreme and a relative extreme, or a local extreme. If you look at this function, it does have a highest possible point, right? So right here, there's our max. Right? The max occurs at b. It's possible for a function to hit the max at many input locations, but there's only one max for this function right there. There's also a min. The min looks like it's the lowest value comes out here. There's our min. Okay. There's a relative max here. So it's not the absolute max. This is the absolute highest the function ever goes. And here's our absolute min. But there's also a local or a relative max right here. Not that it's the highest point, but it's the highest point locally. So near C, this is the highest point. So this is a relative max. Now, something to notice about, let's see, this is the absolute min, right? I just carried it over there, so there's the absolute min right there. Okay, so something about relative or even absolute minima on the interior. If the function's differentiable, can you see that if it reaches a high point, right? So if it reaches a relative max, then it's going to be not climbing anymore, and it's not going to be falling anymore. The derivative can't be positive, and the derivative can't be negative. The derivative has got to be 0 right there if you're at a relative max. So if the name of this function were f, we know at this relative max, f prime is equal to 0. So if that relative max is at c, f prime of c is equal to 0. Here we've got an absolute min in the interior of the interval, and sure enough, the derivative is going to be 0 there, because if you're at a local min, you can't have a negative derivative, otherwise that would mean that you could continue on and go a little bit lower, right? But you can't have a positive derivative, because if you had a positive derivative, that would mean you could go backwards and get a little bit lower. Right at the min, you've got to have the derivative equal to 0 if it exists. Okay, this function is kind of interesting. It has an absolute max, but it doesn't have an absolute min. It looks like it has a lower bound, right? So it has a greatest lower bound, but it doesn't ever achieve that value. So there is no absolute min. So the pattern that we're going to see here is if a function is continuous on an entire closed interval, and this one's not, right? It's not continuous at this endpoint because it's not even defined there, and it's not continuous here. So this one is only continuous on an open interval, not on a closed interval. If a function is continuous on a closed interval, it's got to have an absolute max and an absolute min. But if it's not, then it may or may not have an absolute max and absolute min. Another thing I want to notice is if it has a max in the interior. Here it's not differentiable, but so you can have a max and not be differentiable. But if you are differentiable at a max, the derivative should be 0. So the places in the interior to look at are going to be places where the derivative is either 0 or undefined, maybe because you have a cusp like this or a corner point, something like that. Okay, good. Can you see why there's no lower bound? Because I can see this looks like there's no absolute min, because I can't ever get the lowest possible value. Can't ever figure out what the lowest possible value of the function is. I can't ever get this actual value out. As I move closer to a, they go lower and lower, but they never achieve. They never happen to actually hit that lower bound. So there isn't an absolute min in this case. Here's another one. This one's continuous on a closed interval, although I think my picture has a little gap in here. I'm going to fill it in so it looks normal. Okay, notice that we've got our absolute min is here at one of the endpoints of the interval. It's continuous on the whole closed interval from a to b. and the max occurs at a place where the derivative is 0. At this place where the derivative is 0, that's where the max is going to be. For functions that are continuous on a closed interval, the only place you can have an absolute max or an absolute min, by the way, this is our absolute max, right? Okay, so the only place you could have an absolute max or an absolute min would be either at one of the endpoints, like the absolute min was over here at the endpoint of the interval, or at a place in the interior where the derivative is either 0 or undefined. That's all you got to consider when you have a continuous function on a closed interval. Okay, this function doesn't have an absolute max or an absolute min, does it? So it definitely has, there's a lower bound here, a greatest lower bound, and there's also an upper bound, a least upper bound, but the function never actually achieves those values. You can't ever quite get this value out. You can get really close to a, and so the output will get really close to that upper bound. So the closer I get, and I'm a little bit limited by how straight I can draw, but you can imagine me getting closer and closer and closer, but I can never quite get that value out. So there's no value that we could say that's the highest value that actually comes out of the function. There isn't a highest value in that case. Neither is there a lowest value, can you see, because there's, even though the function is defined at c, this function doesn't have an absolute min. So we can't actually achieve this greatest lower bound because the function is discontinuous there. There's a little hole in it, and it's defined to be some other value up there. Okay, so this just illustrates if you have a function that's not continuous on the entire closed interval, you may or may not have any absolute extrema. In this case, there are no absolute extrema, right? There's not an absolute max, there's not an absolute min, but it's not continuous on the whole interval either. Okay, this function is not continuous on the whole interval, but it does have an absolute max. And it does look like it has an absolute min. I think it occurs at b, right? So there's our absolute min. You can have discontinuous functions can have absolute maxima and absolute can have an absolute max and an absolute minimum, but there's no guarantee that they will, because the previous example showed a discontinuous function, right, that didn't have an absolute max or absolute min. But every time we've seen a function that was continuous on a closed interval, it did have an absolute max and an absolute min, okay, and that either occurred at an endpoint or it occurred at a point in the interior where the derivative was 0. This one has an absolute max for sure, right? You plug in a, you get out the biggest possible value. It also has an absolute min here, so there's the value of our absolute max. It occurs at a, and our absolute min occurs at c. This is the value of the absolute min. This is where it occurs. A lot of times we're not so interested in the actual value of the min or the max as in what should the input be to achieve that. So if we had a function that maybe described our cost, we would want to find the minimum cost, right? We want to know what do we do to make the cost as low as possible. We're not as concerned about what the lowest possible cost is because we're like, well, as long as I'm getting it for the cheapest deal, that's okay. All right, here's a function, but notice it's not continuous at 0, right? So if it's not continuous on the whole interval, you can't be guaranteed that there will be an absolute max or an absolute min, and there's no absolute max in this case, and no absolute min. So, but then again, it wasn't continuous. If it was continuous on a closed interval, there would have to be, and it would occur at either an endpoint or at a point where the derivative was 0 or undefined on the interior. There's an example. It's continuous on the whole interval from -2 to 2. That's a nice closed interval, right? Continuous throughout. And sure enough, there's our max at a critical point, a point where the derivative is undefined because it has a corner, right? So the derivative is undefined right there, and that's where our max is. The mins, the only other place they could be if you don't have any places where the derivative is undefined in the interior, the only other place you could have a min would be on the boundary. In this case, the min is 0, right? There's definitely a lowest value that comes out of this function, but it occurs in more than one place. It occurs at x equal -2 and x equal 2. So if there's going to be an absolute min, there's got to be one single value that's the absolute lowest you can get out of that function. But it could occur in multiple places, which it does in this example. Again, a continuous function on a closed interval has to have a max and a min. Okay, this one has an absolute max, doesn't it? Up here, 5. So the absolute max is 5. Looks like it occurs at 0, I presume. But there is no absolute min. You can keep getting the outputs get closer and closer to 0, but there's never a point where the output is actually 0. So no absolute min. When your function is not continuous on a whole closed interval, it's not guaranteed to have an absolute max and an absolute min. It may or may not. This one has an absolute max but not an absolute min. But if it is continuous on a closed interval, it will have an absolute max and an absolute min. Okay, like this one, it's continuous on this whole closed interval from -3 to 2, and sure enough, it has an absolute max of 2 and an absolute min of -2. Notice that they occur in the interior at points where the derivative is undefined. Undefined because they have corner points. Okay, well, I've been saying this over and over again. It's something called the extreme value theorem. It says if f is continuous on a closed interval a, b, then f attains both an absolute maximum value capital M and an absolute minimum value little m, let's see, on, I would say on that interval, not necessarily in it. So, and where that's either going to be at a place where the derivative is 0 or undefined in the interior, or at one of the endpoints. So what they're saying is that is there are numbers x1 and x2 in the domain, right, in that interval AB, where you can plug in and get the smallest value out, and you can plug in and get the biggest value out, and all the other values are either equal to those or somewhere in between. So for every other point in the interval. Okay, basically it's just saying if you have a continuous function on a closed interval, it's got to have an absolute max or an absolute min. Next thing, if f has a local maximum or minimum value at an interior point, and the derivative is defined, then the derivative has to be 0. And we saw that in lots of examples. If there was going to be a local max, if the derivative was going to be defined, it would be 0. It's also possible that you could have a local max because the derivative is undefined. Those are really the two cases. So here f prime is 0 or f prime is undefined. We can't figure out what the value is because there's a corner point, so we don't have the limit that defines the derivative doesn't exist at that point. So if you're going to have a local max or min, that's got to be the derivative has to be equal to 0. So all that really counts in the interior are places where the derivative is 0 or undefined, right? We call those critical points. Those are the only places we need to check other than the end points. And so if we have a function and we know it's continuous on a finite closed interval, so all bets are off if you have an interval that goes off to infinity, but as long as it's finite closed interval, so you have A and you have A and B, and you're containing those two finite endpoints, then you know that there's going to be a max or min by that theorem 1, and so all you got to do is check the critical points, places in the interior where the derivative is 0 or undefined, and the endpoints. You can have a max at an endpoint, right? Even though you don't have a full derivative at those endpoints. So you just check all those places. Whichever one gives you the highest output, that's got to be the max, and whichever one gives you the lowest output, that's got to be the min. So we'll now do several examples where we find those absolute extreme points in those cases.